Hello, welcome to another module in this massive open online course. So in this module, let us start looking at another very important concept, and that is related to decomposition of any matrix, and this is known as the singular value decomposition. All right. So in this module, let us start looking at a new and a very important concept, and that is of the SVD, which basically stands for the singular value decomposition. Singular value decomposition, which is a very important decomposition. It's a very important concept, and the SVD, the singular value decomposition, is defined for any matrix. Not necessarily square, not necessarily square. This is an important thing to remember, because the eigenvalue decomposition, remember, is defined only for a square matrix, but the singular value decomposition is defined for any matrix, any arbitrary m cross n matrix that is not necessarily square. Okay. So consider H, which is an m cross n matrix. Remember, I think at this point it is worth remembering that the eigenvalue decomposition is defined only for a square matrix, that is only for square matrices. Okay. So consider H to be any matrix m cross n matrix. For ease of visualization, we will just consider m greater than or equal to n, right, and the case where m is less than n is similar, right. So let us consider a tall matrix m cross n matrix where m is greater than or equal to n. So I can write such a matrix as, it looks like this. So m equals number of rows, and if you look at n, this is equal to number of columns. Number of rows is greater than or equal to number of columns, which implies that this is a tall matrix, right. So that is our nomenclature. Okay. And the singular value decomposition, SVD, is given as H equal to U sigma V Hermitian, where U can be written as an m cross n matrix, sigma can be written as an n cross n matrix, and V Hermitian can be written as an n cross n matrix, and this looks like follows. So H equals the singular value decomposition. So you have m cross n matrix U, so that is U1 bar, U2 bar, UN bar, so it has n columns. Then you have the diagonal matrix sigma 1, sigma 2, sigma n, which is n cross n, and then you have V Hermitian, which comprises of the rows V1 bar Hermitian, V2 bar Hermitian, Vn bar Hermitian. So this is your matrix U, this is your matrix sigma, and this is the matrix V Hermitian. Okay, so these are the components of the singular value decomposition. Okay, so this is basically how the singular value decomposition looks for a tall matrix H with m greater than or equal to n, right? And now let us now start looking at the properties of the SVD. Okay, so what are the properties of the SVD? Properties of the SVD, that is, if you look at these vectors u1 bar, u2 bar, so on, un bar, u1 bar, that is, if you look at the vectors u1 bar, u2 bar, so on up to un bar, these are orthonormal vectors. These are orthonormal vectors, which essentially implies that each is unit norm, that is norm ui square equal to 1, and orthogonal, which means ui bar Hermitian uj bar equal to 0 for I not equal to 0. Okay, so this is an orthonormal set of vectors, and therefore this implies, naturally this implies that if you look at the matrix product U Hermitian U, right, this implies that U Hermitian U, this will be the identity matrix of size n cross n, and U is therefore this is known as a semi unitary matrix. So, the matrix U contains orthonormal columns u1 bar, u2 bar, un bar, such that norm of each ui square is ui bar square is unity, and ui bar Hermitian uj bar equal to 0 if I is not equal to j, and therefore the matrix U Hermitian U is identity. And these vectors are known as the left singular vectors, that is, these vectors u1 bar, u2 bar, un bar in the singular value decomposition, which are in the matrix U on the left, are known as the, it's self explanatory, these are known as the left singular vectors. Now, what are these left singular vectors? It is not very difficult to see that if you look at H, we will look at that again. Okay. Now, let us come now to the property of V. What about the matrix V? Now, similarly, if you look at V, V1 bar, V2 bar, Vn bar, this is an n cross n matrix, which implies is a square matrix, right, and V can be written, and V also contains again, now these are known as the right singular vectors. Naturally, these are part of the vectors of the right, these are known as the right singular vectors, because these are in the matrix V bar, which is on the right, and these are also, if you look at V1 bar, V2 bar, Vn bar, these are also orthonormal, which implies norm Vi bar square equals unity, and Vi bar Hermitian Vj bar equal to 0 for any I not equal to j. Okay. So, Vi bar Hermitian, Vj bar, so these are unit norm as well as orthogonal. Okay. And therefore, the matrix V satisfies the property V Hermitian V is identity which also implies V Hermitian equals identity because V is a square matrix. Reason being, if for a square matrix B the inverse is unique and the left inverse is same as the right inverse, that is, if AB is identity, then BA is also identity. So, V Hermitian is identity implies that V Hermitian into V should also be identity, and therefore, V is a unitary matrix. Okay. Because it is a square matrix, V is a unitary matrix. And the matrix sigma has an interesting structure. Now, we come to sigma, which is essentially, you can write this as sigma equals sigma 1. This is a diagonal matrix. Now, these are termed the sigma i's, these are termed the singular values of H, just like the eigen values, we have the singular values of H, and these sigma i's are all greater than or equal to 0, these are real and greater than or equal to 0. So, sigma i's are non negative, that is, they can be 0, but they cannot be less than 0. Okay. And also important to note that the singular values have to be arranged in the decreasing order of magnitude, right. Sigma I 1 greater than or equal to sigma 2 greater than or equal to sigma n. So, singular values are arranged in decreasing order of magnitude. These are arranged in decreasing order of magnitude. And the other important thing here is the number of non-zero singular values. Equals the rank of the matrix H. That is, if you have the singular values sigma 1 greater than or equal to sigma 2 greater than or equal to so on sigma p and sigma p plus 1 onwards, if they are 0, that is, if you look at sigma p plus 1 equal to, and these are, let us say, zeros, these are essentially non-zero. This implies that rank of H equals, this implies that the rank of the matrix H is equal to P, number of non-zero singular values of H, the number of non-zero singular values of H is equal to basically the rank of the matrix H. Okay. And well, what is the relation between the singular vectors and singular value decomposition and the eigenvalue decomposition? That is also interesting. So, if you look at H equals U sigma V Hermitian, So, consider H Hermitian, that is U sigma V Hermitian times V sigma U Hermitian. V Hermitian V, this is equal to identity. So, this reduces to U sigma square into U Hermitian. So, this implies that the ui bar are eigenvectors of H Hermitian, right. You can clearly see this is the eigenvalue decomposition, and sigma square, that is sigma square, the diagonal, these are the diagonal elements of the matrix sigma square, these are the eigenvalues of H Hermitian, that is the singular values of H, the square of the singular values of H are the eigenvalues of H Hermitian, or you can also say that the square root of the eigenvalues of H Hermitian are essentially the singular values of the matrix H. Okay. Similarly, if you consider H Hermitian H, so what this shows is the left singular vectors ui bar are eigenvectors of H Hermitian. Now, similarly, consider H Hermitian H, this is essentially V, right, this is V sigma U Hermitian U sigma V Hermitian, which is V sigma square V Hermitian, because U Hermitian U is identity, which implies that Vi bar, these are eigenvectors of H Hermitian H, and sigma square are the eigenvalues of H Hermitian H. Right. So, sigma square are also the eigenvalues of H Hermitian H, right. So, the ui's, the vectors ui bar are the eigenvectors of H Hermitian, Vi bar are eigenvectors of H Hermitian H, and sigma square are essentially eigenvalues of both H Hermitian and H Hermitian H. Okay. And let us look at some other interesting things about the SVD. Let us now compute the pseudo inverse in terms of the SVD. So, we have the pseudo inverse as we know, for a tall matrix, this is given as H Hermitian, H Hermitian H inverse H Hermitian. Substitute for H in terms of the singular value decomposition, this is V sigma U Hermitian U sigma V Hermitian inverse times H Hermitian, that is V sigma U Hermitian. So, this becomes, if you look at it, this becomes V sigma square V Hermitian inverse V sigma U Hermitian. So, this becomes V sigma square V Hermitian inverse. So, this is V Hermitian, sigma square inverse is sigma raised to minus 2, because V Hermitian inverse is, so V Hermitian inverse is V. So, that becomes, so you can write this as follows, just write an additional step to make it clear. V Hermitian inverse sigma square inverse is sigma raised to minus 2, this is V inverse times V sigma U Hermitian, but V Hermitian inverse is V. So, this is V sigma raised to minus 2, V inverse V is identity times sigma times U Hermitian, which is essentially equal to, so H pseudo inverse is essentially equal to V sigma minus 1 U Hermitian, where sigma minus 1 naturally is a diagonal matrix with the elements as 1 over sigma 1, 1 over sigma 2, 1 over sigma n. Alright, so this is essentially the pseudo inverse of H. The pseudo inverse of H in terms of the SVD, in terms of the singular value decomposition. Pseudo inverse of H in terms of the singular value decomposition. Alright, so this is basically, if you look at it, this is basically the structure and the properties of the singular value decomposition, rather the different matrices, the different component matrices of the singular value decomposition. Let us now look at a simple example to understand this, kind of a paper and pen example of the singular value decomposition. So, let us look at, of course, the singular value decomposition typically is not easy to compute by hand, but let us look at a simple, let us try to do this via a simple example to illustrate this. So, you have H, let us consider H, which is the following matrix. So, the H is this 4 cross 2 matrix. So, it is a tall matrix 4 cross 2. Now, you can see, now let us ask the question, what is the SVD of this? Now, you can see ordinarily it is not very easy to evaluate the singular value decomposition, but in this case there is an interesting property. If you observe closely, the columns of H are orthogonal, and therefore, it is almost similar to the structure of the matrix U. Alright, so we can take advantage of that to evaluate the singular value of the decomposition of this in a rather easy fashion. Okay. So, what is the point here? The columns of H are orthogonal, and therefore, it is similar to U, but except columns of U are orthonormal, right. So, we have to normalize the columns of H, alright. So, you look at this, this is your H1 bar and this is your H2 bar. We have to perform H1 bar divided by norm H1 bar, and that will become our U1 bar, and H2 bar divided by norm H2 bar, that will become our U2 bar. So, what is norm of H1 bar? Norm of H1 bar is under root of 1 plus 1 plus 1 plus 1 equal to under root of 4 equal to 2. Similarly, norm of H2 bar equals under root of 2 square, which is essentially 4 plus 4 plus 4 plus 4 equal to under root 16, which is equal to 4. Okay. And therefore, I can write H after normalizing the columns as, well, that will become 1 divided by 2, 1 divided by 2, 1 divided by 2, 1 divided by 2, 2 divided by 4, minus 2 divided by 4, minus 2 divided by 4, 2 divided by 4 times, now the diagonal matrix, first column has to be multiplied by the norm 2, second column has to be multiplied by the norm 4, which is essentially equal to, now simplifying this, half, 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 minus half, minus half, half, and times 2, 4, 0, 0. And now you can see this is your matrix U, and this is your column U1 bar, and this is your column U2 bar, and you can see they are orthonormal, that is U1 norm U1 bar square equal to norm U2 bar square equal to 1, U1 bar Hermitian U2 bar equal to 0. Okay. And therefore, and now you can see this is very similar to sigma. This is, I am not saying this is equal to sigma, but this is similar to sigma. So, all I need is V. I can insert the V as follows. I can write this as the identity matrix. So, this is unitary. Now, this is V, right, because V into V Hermitian equal to V Hermitian V equal to identity. Sigma is a diagonal matrix, non-negative, the diagonal elements are non-negative. The problem here is the diagonal elements are not arranged in decreasing order. So, therefore, this is not a valid SVD, because if you look at the diagonal elements, sigma 1 is 2, sigma 2 is 4, so sigma 1 is less than sigma 2. That is the only problem here, alright, except for that. So, sigma 1 and this is sigma 2. So, sigma 1 equal to 2, sigma 2 equal to 4, sigma 1 less than. So, if you look at this, we have sigma 1 equal to 2, sigma 2 equal to 4, and therefore, sigma 1 less than sigma 2 implies this is not, hence this is not a valid SVD, not a valid SVD. So, all we have to do is essentially we have to, if somehow we could switch the diagonal elements, instead of 2 we had, place of 2 if we had 4, in the place of 4 if we had 2, this would be an SVD, and we can do that right away by doing a simple trick by switching the columns and rows alternatively. So, I have H equals, let me write this once again and let me illustrate what can be done here. It is simply a permutation of the columns and rows. So, you have A half, 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 minus half, minus half, half, times you have 2, you have 4, 1, 0, 0, 1. Now, what I am going to do is I am going to switch the columns of this and correspondingly switch the rows of this, that will leave the product unaltered. So, this is going to become, switch the columns of the first matrix and the rows of the second matrix, half minus half, half minus half, 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 and here I am going to write 0, 4, 2, 0, 1, 0, 0, 1. Still not in the form, in fact, it is worse because this diagonal have become off diagonal elements. Now, all I have to do is perform switch once again the columns of the middle matrix and the rows of the last matrix. So, this is going to become now, this is going to become your half, 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 minus half, 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 switch the columns, this becomes 4, 0, 0, 2, and switch the rows, this becomes 0, 1, 1, 0, and now you can see this is a valid singular value decomposition. So, this is your matrix U, this is your matrix sigma, this is your matrix V, we have U Hermitian, U is identity, right, V Hermitian equals V Hermitian V equals identity, and we have sigma is diagonal with sigma 1 equal to 4, sigma 2 equal to 2, and they are arranged in decreasing order, right. So, these are in decreasing order. So, that is a simple example. As I already told you, in general it is not easy to evaluate the singular value decomposition via hand, but in this case, because H has an interesting structure, we have exploited that to rather easily come up with the singular value decomposition, right. So, in essence, once again, the singular value decomposition, just like the eigenvalue decomposition, in fact it is more useful, I can say, in certain ways than the eigenvalue decomposition, because the eigenvalue decomposition is defined only for square matrices, whereas the singular value decomposition is defined for any matrix H of an arbitrary size m cross n. In particular, we have shown this for the scenario where m is greater than or equal to n, but you can readily also see what the counterpart is going to be if m is less than n, alright. And we have described the components, that is the U sigma V Hermitian, the properties of each of these components, the U matrix, V matrix and the sigma matrix, and finally looked at a simple example to understand this better. Alright. So, please, as I have already told you, singular value decomposition is very significant and has many applications throughout. In practice, talk about signal processing, wireless communication, machine learning, data analysis, I mean there are a large number of applications, and it is in fact I would like to say one of, along with the eigenvalue decomposition, probably one of the most widely used tools in modern scientific analysis. So, please go through this again and try to understand and appreciate this concept better and understand it thoroughly. Thank you very much.